So I will start with a brief recap of our previous computations. If you remember well, first of all, we computed correlation by classic procedure. So it means in chess regression and correlation. And the value of the correlation was approximately minus 0.617. This correlation was computed for depression and well-being variables. So it is quite strong negative correlation. Then we started to compute the same step by structural equation modeling. So we applied this procedure SEM, structural equation modeling. In this procedure, there is no clicking platform, but it is necessary to add commands which are describing the model. We are using here Lavan package from R, and correlation or covariance is written as the first variable, then double tilde or double wave if you like, and the second variable. And if you apply this classical model, structural equation model to correlation, so you will get descriptive results. So it means the result must be the same as for classical correlation procedure. So if you go to the first row of parameter estimates table and you visit a standardized result, here it is, standardized all. So this value is the same as we have described by classical correlation procedure. Unfortunately, for this classical correlation model, there is no option for testing in structural equation modeling as degrees of freedom are 0. And for models that have 0 degrees of freedom, there is no space for testing, as chi-square distribution for 0 degrees of freedom is not defined. So it is impossible to compute p-value, and it is also nonsense to evaluate the rest of statistics which are hidden here in tables, such as user model versus baseline, root mean square error approximation, etc., etc. So, as this is impossible to test for this model, so we decided to move on and to test some expected value. For example, from previous study, we have some recognition that the correlation could be approximately minus 0.6, and we would like to test that still it is the value which is valid for our population. So if I like to test some specified values through structural equation models, I must implement this pre-specified value into the model. Unfortunately, it is impossible in chess to specify correlation, but we need to recompute correlation into covariance. From previous lecture, you know that this equation, correlation and covariance, are closely related. So it means if you like to compute covariance from correlation, you would take correlation and multiply by standard deviation of both variables. So minus 0.6 multiplied by standard deviation of the first and the second variable, it means well-being and depression, would get the value of covariance, and this covariance was approximately minus 0.1052. And that's why it is written here. So if I like to test specified value of some parameter, I would add it to the model as the value. So here, well-being double tilde, the specified value for covariance multiplied by depression. And this is the trick, I would call it, how we can start to test correlations via structural equation modeling. So here we are testing whether correlation could be minus 0.6. And if I sum up very briefly basic results, so we can see that we have received 1 degree of freedom, as we are saving 1 degree of freedom by fixing the value of covariance or correlation. So here it is. Here is the value of covariance. Here is the value of pre-specified correlation. And if we apply the test, chi-square test statistic is very, very low one, 0.117. The border for statistical significance would be approximately 4, or more precisely 3.84. So this is far below this threshold, and the p-value is 0.732. Once again, I would like to recap the basic logic for this chi-square test. Null hypothesis say that our model and my data are close to each other, or in another words, the null hypothesis says that covariance matrix which can be seen from my data is the same as covariance matrix which is generated by my model. So these two are closely related. Alternative hypothesis, of course, is just opposite. So it means that my model doesn't fit to my data. And as p-value is quite big one, so that's what we would like to see in structural equation models, we conclude that there is no space for rejection of our model, and it is possible that correlation for well-being and depression could be minus 0.6. We have also briefly covered discussion about alternatives to chi-square test in structural equation modeling, such as CFI and TLI. They should be at least 0.9. This is a rough recommendation. Root mean square error of approximation should be ideally below 0.08, and also the next measurement of, let's call it error in our model, which is called standardized root mean square residual, SRMR, should be below 0.05. So all these thresholds are flowed here, and it's not big surprise if chi-square test is statistically insignificant. It seems that our model should be correct. Once again, recap of weakness of this chi-square test. So if my sample is big, at least in many hundreds and thousands of units, and if my model is quite complex, this chi-square test is too sensitive, and usually the result would be small p-value, so it means rejection of our model. It is usually not the sign that my model is not correct, but it is usually only artifact of this previous discussion. It means big sample size or complex model. That's why instead of this chi-square test, we are mostly using these criteria such as CFI, TLI, RMSEA, etc., etc. So we will be discussing these criteria repeatedly in this course. So this is a brief recap of previous lecture. And now I would switch into the JASP presentation. And now we will move to regression topic. So before we start, only a formal description. If I'm discussing about correlation, I am using two tildes. If I'm discussing about regression, I am using dependent variable, then one tilde, and then the same style as for regression equations. So it means the first predictor plus second predictor, etc., etc. So this is the description of regression model via structural equation model. If I move on briefly, so we will go to the slide number 11. And first of all, we will compute classical regression model in structural equation models, so without no fixing, and our model will be based on flowing computation. So once again, here this data matrix. So we would be computing relationship on well-being, on social support, and proactive coping. It is expected that well-being is positively related to both of these phenomena. So it means to social support and proactive coping. So it is expected that both these regression coefficients would be positive. If I go back into the description of the model in JASP, so it is expected that I would type well-being, WB, tilde, then social support as S, plus proactive coping PC. So this will be my model for regression for the first insight. So first of all, I would skip into structural equation models, so SEM and structural equation modeling. And first of all, I will change slightly title. So I'm computing regression, and no fixing currently is available. So once again, I would type well-being WB, then double tilde. If you cannot, single tilde. If you cannot find it, you can go to the presentation slide number 8, where you can copy the symbol of tilde. Then social support SS plus PC as proactive coping. So once again, I would copy this equation to the presentation. So here it is. So this is my regression equation for today. So here it is. This blue formula is the formula for which we will compute result. So if you like to run results, first of all, it is maybe good to add some outputs. So I would ask for statistics, for additional fit measures. These are the CFIs, TLIs, etc. And maybe we can also go to options, but I guess there is no more necessary output. No, we don't need it. And if you like to see the picture, but I wouldn't ask for the picture here, you can ask also here for path diagram. So if you like to run the model, you need to click into this big window for Levant syntax, and Control plus Enter is the correct running command here. So once again, yeah. So JASP computing. And before we start to discuss, I would like to warn you that if we are computing this, I would call it full regression model, we would get the same problem as for correlation. So it means we would get 0 degrees of freedom and no option for testing. So we would need in the next step, and this is slide number 12, some fixing in the model. So I would go back. Here we have our results, and these results confirms our expectation. So you can see 0 degrees of freedom, and of course no p-value. So it means no evaluation. And why is it so? So as the input for my computation, I have 1, 2, 3 variables. So if I take it from structural equation modeling perspective, I am using 1, 2, 3 variances. I'm also using 1, 2, 3 covariances. So I have 6 pieces of information as the input. And if I'm applying general regression model, I'm also computing the same stuff as you can see it here. 1, 2, 3 variances. This is SS double tilde SS PC double tilde PC and well-being double tilde double VB. So these are 3 variances. There is also one regression coefficient, second regression coefficient, and there is also covariance for predictors. So this is this row SS double tilde PC. So it is expected in classical regression via structural equation modeling that also predictors are correlated. So 6 pieces of information as input, 6 pieces of information as output. So there is no space for testing, 0 degrees of freedom. So these results, once again, so it means these coefficients or standardized coefficients are only, let's call it, descriptive statistics. For us, maybe it could be interesting that if you check the values of regression coefficients. So these are regression coefficients 0.329 and 0.357. They are quite close to each other. So it means that the impact of social support and proactive coping on well-being is nearly the same. And from previous study, and we are here only replicating some previous study, it was shown that these two impacts are the same. So now I would add to my regression model some style of testing, and I would test that these two coefficients for x1 and x2, in my case, they are called as social support and proactive coping, could be the same. And the easiest style of this fixing is based on added letter, the same letter, which says these two parameters, so it means these two regression coefficients should be the same. So if I type the regression equation in Lavaan and I'm using the same letters for two or more parameters, these two or more parameters would have the same value. So the same name means use the same value, estimate only one value. I am using, once again, fixing, but not fixing on some pre-specified value, but I am fixing two or more parameters to be the same. So this is another style of fixing in structural equation modeling. So now I would recompute my result, and I would expect that these two coefficients could be the same. They are not the same in my sample, but I'm trying to check whether they could be the same in the population. That's the meaning of statistical testing in general. So now let's have a look how it works. So I would once again take this pre-specified regression. I would make copy from this procedure. So clicking on this green plus, I would change only title briefly, sorry for that. So once again, so I would change the title. So regression, fixing of parameters. At the same level. So here it is. And I would only need to change slightly the description of my equation. So before social support and before proactive coping, I need to type the same symbol. The easiest symbol is letter B, as we have it here. So I would only change it here for this equation. So here I would type B multiplied by PC and social support together. So now I'm slightly changing previous equation by the same symbol for two regression coefficients. So B multiplied by individual predictors. So I would type it here directly into JASP. So here is the first part and second part, and I can once again click Control plus Enter. Once again, if I am preparing this fix, so it means equality of two parameters, here I am saving 1 degree of freedom. So it means I would get 1 degree of freedom for testing, and this model could be once again tested. So let's check it in JASP, and you can see that it is really true. You can see 1 degree of freedom. Chi-square test criteria is quite low, and I guess that you can help me to evaluate this model. If p-value is 0.749, what does it mean? Is it possible that these two regression equations, coefficients are the same or not? What could be my conclusion here?
They are not.
Once again, p-value is quite big one. What does it mean in structural equation model if p-value is quite big? What are hypotheses behind this test? So once again, null hypothesis says that the model fits to my data, an alternative that it doesn't fit to my data. So what will be conclusion here? Is my expectation, my model, that these two coefficients are the same or not possible, valid or not?
We accept null hypothesis.
Sorry, we don't accept, we say that we don't reject. That's a correct conclusion. But we are not able to reject our expectation that these two coefficients could be the same. Yeah? Do you agree?
Yes.
Okay. So it's possible that these two coefficients could be the same. You can check that these two coefficients are the same. So it means that Lavan, or just through Lavan, estimated these two coefficients only by one value. These two rows are the same as it was estimated only once as common impact of social support and proactive coping on well-being. Here you also can find once again the label. So we are assigning these letters to the coefficients. You can find these letters in label column. This is quite classical style in structural equation model software packages that for individual parameters we can use labels. So here it is, and label here is B and B, and it means it would be the same value. So once again, the main goal here was I would like to test if these two coefficients could be the same. And once again, if our data file would be bigger and if our model would be more complex, this chi-square test wouldn't help us to evaluate the model. So that's why we would skip to next parts of the output, and we would evaluate CFIs, TLIs, etc., etc. So I would go through it only very quickly, as we don't need it here, but only once again to recap. So these statistics from this first table, CFI, TLI, NNFI, EFI, RNI, etc., should be big values. Usually thresholds that are recommended are approximately 0.9, sometimes 0.95. So as you can check here, these thresholds are followed by my model, so it seems good for this example. Once again, just opposite is the statistics, which is called RMSEA, which is measuring some error of my model. And once again, recommendation, which is usually followed in the literature, is that this statistic should be below 0.08. Here it is closely to 0. So once again, no problem can be seen in my model. And the last one, statistics, SRMR, sorry for that, 0.05 is usually recommended threshold to be lower than this value. And here it is 0.005. So once again, this threshold is fulfilled. So once again, this is the sign of the quality of my model. So I can be sure that this model could be quite good for my data, and I can apply this model, and I can expect that these two coefficients could be the same. One more discussion point about this model. So this model is evaluating the impact of social support and proactive coping on well-being. This is the most important part of this model. So it means that both of these influence by the same amount well-being. So that's my main conclusion. But I can also evaluate another parts of the model. Maybe it would be quite good to discuss briefly about the meaning of this well-being, double tilde well-being. If I go back two pictures from our current presentation. So if I go back here to our regression case, so we know that for every dependent variable, there is some random error. And this description, well-being and well-being covariance, is not nothing more than the description of variance of this random error. And if I go to this third row of this parameter estimates table, so it means this is the variance of this well-being unstandardized and standardized. Here is the standardized version. So here I can see that standardized variance of this variable, so it means once again this random error of dependent variable is 0.801. And this is the measurement of unexplained variance. So it means unexplained variance by my regression model, well-being on social support and proactive coping, is approximately 81%. So it means that the level of explained variance is, can you help me, if unexplained is 81? What could be the value of explained variance? 100 minus 81. So it will be approximately 90. 19. If I would like to check it, I can go to statistics and I can ask here for R-squared statistics. So this is the same style as for regression. Just would add one more table into my output. So if we wait a minute, so we would get a new output here and you can check it. Where is it? This is the table and you can see 0.19. So it seems correct. If we discussed here that 81% is unexplained and 19 are explained, the proportion of variance. So this is the meaning of this symbol, dependent variable, double tilde, dependent variable. Once again, this is the variance for random error, which is related to dependent variable in structural equation models. And there are also variances of proactive coping, social support, and there is also correlation or covariance for two predictors here. So it means that the correlation between social support and proactive coping, it is standardized version of the coefficient, is 0.3. Of course, if you like, you can test individual parameters here. So it means these regression coefficients are tested here by a formal test, which is based on estimate divided by its standard error. The result is approximately normally distributed. That's why Z is described here, and p-value is recomputed for these Z statistics. So it means that this impact of social support and proactive coping is statistically significant. And from substantive point of view, I can evaluate these unstandardized coefficients or standardized coefficients if I like to describe the relationship for well-being and social support. So it means that if I add one more point to social support scale, well-being would increase by 0.34 approximately. If I would like to use standardized version of the coefficient, so the interpretation would be, if I add one standard deviation of social support, I would get increase by 0.3 to approximately of standard deviation of well-being. So this is for interpretation in standard deviations. This is the interpretation in original units, the same style as for classical regression. So that's regression staff and style of fixing and evaluating of real examples through structural equation models. So I would go back once again to our presentation. Here we are, slide number 13, and we are summarizing description of regression through structural equation model. So if I would like to evaluate a regression model in structural equation model, there is only one option. I must need to specify some value of the coefficient, or I must add some condition of equality of 2 or more parameters. Then it is possible to get positive degrees of freedom and to test the model. If there is no fix, the model couldn't be tested as we have 0 degrees of freedom. And for my results, the most important results are unstandardized coefficients or standardized coefficients. So it means these standardized coefficients, once again here, the column standardized all are the same as beta coefficients for classical regression. One more comment related to these tables. By default, JESP also include here confidence interval. It means lower and upper bound for confidence interval 95% for these unstandardized estimates. If you like to change these settings, you can also change here error calculation into robust and bootstrap, and this confidence interval and also test would slightly change, but there is no option here to change that the level for this confidence interval is 95%. So that's all for this brief introduction. So currently I would stop here recording.